Hello, this will be a demonstration of Proposition 11 from Book 4 of Euclid's Elements, which requires us to, in a given circle, inscribe an equilateral and equiangular pentagon. I might combine the two terms equilateral and equiangular into just regular, so we call polygons which are both equilateral and equiangular, we call these polygons regular. So if I ever call it a regular polygon, you'll know what I mean. We begin, of course, with our circle. You're given a circle A, B, C, D, E, like so. And the task at hand for us is to inscribe a regular pentagon within this given circle, A, B, C, D, E. We begin kind of non-intuitively by actually making a triangle. We're going to make a triangle according to the previous proposition. It's actually 410. Mess that up. We're going to make the triangle FGH like so that the angle at F is half the angles at G and H, or in other words, these base angles right here are equal to double the remaining angle. We showed how to construct such a triangle in the previous proposition for 10, so we're going to use it right away. Next, we inscribe a triangle within this circle such that the triangle is equiangular to this triangle FGH. So let's do that. That'll look something like this. So we're going to have the triangle ACD, like so that the angles ACD and ADC are equal to the angles G and H, and that the angle here at F is equal to the remaining angle CAD. We do this by proposition 4-2, which allows us to inscribe a triangle in a circle such that it's equiangular to a given triangle. So that's what we're doing here. And so given that this triangle is equiangular with this triangle, the triangle ACD is equiangular with the triangle FGH, we know that the angles ACD and ADC are equal to double the angle ACD. Next, we bisect these base angles at C and D. We do this by 1, 9. We're going to bisect the angle ACD with the straight line CE. And again, by 1, 9, we're going to bisect the angle ADC with the straight line BD, like that. Right? So these angles here are going to be equal. So that's what it means to, bisect an angle. Okay. And we end this by joining the straight lines AB, BC. We don't have to join CD, DE, and EA. So what we're going to prove is that this pentagon ABCDE is both equilateral and equiangular. This pentagon ABCDE is regular. We begin by noting that the angle CAD is half the angles at ACD and ADC. Again, because it's equiangular to this triangle, we know that the angles within this triangle ACD must be, it's the same sort of situation. So these angles at the base are double the remaining angle, just as these angles at the base are double the remaining angle in this other triangle. Okay. Now, not only is this angle right here half of these angles, but these angles right here, so ACE and ECD, and likewise ADB and BDC, these are also halves of the angles ACD and ADC respectively. So that means that all 5 of these angles, CAD, ACE, ECD, CDB, and BAD, are all equal to one another because they are all halves of equal angles. And again, we know that halves of equal things are equal to each other, and so all 5 of these angles being halves of equal things are going to be equal to each other as well. Now, all 5 of these angles being equal, we can say by proposition 326, which tells us that equal angles stand on equal arcs. Excuse me, that cut out. we know by proposition 326 that equal angles stand on equal arcs. And so all 5 of these equal angles, the arcs which they stand on, must naturally be equal as well. And this means that the arc AB is equal to the arc BC, is equal to the arc CD, is equal to the arc DE, is equal to the arc EA. So all 5 of these arcs, AB, BC, CD, DE, and EA, are all equal to each other. And furthermore, by proposition 329, that equal arcs are cut off by equal straight lines, or equal arcs are cut off by equal chords, we know that the straight lines AB, BC, CD, DE, and EA must also be equal to each other because they cut off these equal arcs. And so knowing that AB, BC, CD, DE, and EA are all equal to each other, we can say that the whole pentagon ABCDE is equilateral. All of its sides are equal to each other. Next, we're going to prove that this pentagon is equiangular, and this is actually fairly easy. We begin by noting that the arc AB is equal to, for example, the arc DE. It's not particularly important which arcs you say are equal, but just pick any 2. And so AB is equal to DE. We had shown that in the previous step right there. And so if we add the same arc to both of these, we know that the whole arcs which result will be equal to each other. That's common notion 2. Adding equals to equals, wholes will be equal. So if we add the arc BCD to both the arcs AB and DE, we can safely say that the whole arc ABCD, so this whole arc right here, is equal to the arc EDCB, right? So these 2 arcs right here, ABCD and EDCB, are equal to each other. Again, by common notion 2, we can say this. And using another proposition from book 3, and that's sort of like stretch of propositions, 26 or 29 are kind of a unit. So using another one, we're going to use proposition 327, which tells us that upon equal arcs stand equal angles. So given these equal arcs, A, B, C, D, and E, D, C, B, we know that whatever angles stand upon them must also be equal, which means that the angle BAE, so this angle BAE stands upon this arc EDCB, is equal to the angle AED, so this angle right here, which stands upon the arc ABCD. Takes a little bit of figuring out the drawing to recognize that, but this angle right here, BAE, I'm going to do 3 lines for it, is equal to this angle AED right here, right? Because they stand upon equal arcs, so by proposition 327, they have to be equal. Okay, now we can prove in a similar sort of manner that the pentagon ABCD has all of its interior angles actually equal to each other. So the angle ABC is equal to the angle BCD, is equal to the angle CDE, is equal to the angle DEA, which means that this pentagon ABCDE is not only equilateral, as was proven in step 3, but now has also been shown to be equiangular. And it is, of course, inscribed inside the given circle ABCDE, right? All of its vertices lie on the circumference of the circle. So we've actually done that which we set out to do. In our given circle, ABCDE, we have inscribed the equilateral and equiangular pentagon ABCDE. So that means we're done with the proposition QEF. I've, nothing special to say about this proposition. It's quite cool. I like constructing regular pentagons. There is an easier way to do this that you can probably find just by looking up proposition 411. At least that's how I found it. So you can just kind of draw regular pentagons, very easily, like just kind of on a whim if you have a straight edge compass. I think that that's quite fun. So other than that, I've, nothing to add to this proposition, nothing further to explain. I've gone through it all. So I'm going to end the video here and move on to proposition 412.